My name is Lee. Today I will present our paper, Maintaining Social Links through Amplify-and-Forward in Wireless Networks. In the past decade, various routing techniques have been proposed for mobile ad hoc networks. For example, in a sparse mobile ad hoc network, while the node density is low, carry and forward is used, while the nodes physically carry the data, then forward the data to nodes with higher forwarding probability. Recent research also exploits social knowledge to improve the performance of data forwarding. Because social knowledge is more reliable and less susceptible to node mobility. However, although these works have used social knowledge to improve the data forwarding performance, most of these works have focused on improving the data forwarding for all the nodes in the network. We have observed that in real scenarios, the communication between some of the node pairs might be more important. In such a case, the underlying communication network should try to maintain the communication between those important social pairs, even at the cost of sacrificing the performance with other nodes. Let's consider a battlefield scenario where there is a squad of soldiers and also a commander. Apparently, we should try to maintain the connection between the squad leader and the commander. In this way, the commander can receive the most up-to-date reports from the squad leader. The squad leader can also get the commands from the commander. On the other hand, the connection between the soldiers and the commander are much less important, and it is unnecessary for us to maintain good connection between the commander and each of the soldiers. There are many research challenges to maintain the connection between the important social pairs. Let's still think about the battlefield scenario. So let's say if the squad leader and the commander are quite far away from each other. In this case, the network partition is possible, and there is no routing path between the squad leader and the commander, and MobiHoc transmission may not work well in this case. To address such difficulties, in our paper, we adopt an amplify-and-forward strategy. The basic idea of the amplify-and-forward strategy is that we have the nodes or the relays in the network cooperate to improve the signal strength at the destination. I will present more details of this strategy in the next slide. So in this amplify-and-forward strategy, it takes two steps for the source node to transmit the signal to the destination node. In the first step, the source node will broadcast the signal to the nearby relay nodes. And after the relay nodes have received the signal, in the second step, the relays will try to amplify and forward their received signal to the destination. The following figure gives an example on how this strategy works. So basically, the source node will first broadcast the signal to those relay nodes. And then, after the relay nodes receive the signal, they will amplify and forward their received signal to the destination. In this way, the destination will be able to receive a much stronger signal, which is the sum of the signals sent from node B, C, and D. As we involve more and more relay nodes in this transmission, we can imagine that the signal strength at the destination can be further improved, and consequently, the connection between the source and destination node can be maintained. To investigate how this amplify-and-forward strategy can be used to maintain the connection between the important social pair, we consider two problems in our paper. The first problem is called mean energy problem. Because we know that the energy at each of the relay nodes is limited, so the mean energy problem here tries to minimize the power consumption at the relays while maintaining the important social links. The solution of this mean energy problem minimizes the power consumption at the relays. But the problem here is that in the solution, all the relays will be involved in the transmission. This means that this will cause a significant synchronization overhead because all the relays need to synchronize their clock so that their signals can be sent to the destination simultaneously. So to reduce such synchronization overhead, in the mean relay problem, what we want to do is we want to minimize the number of active relays while maintaining the important social link. Let's first look at this mean energy problem. We use N to denote the number of relays in the network, and we use Pi to represent the transmission power of relay I. Then apparently for our mean energy problem, the objective is to minimize the sum of the Pi. And for the first constraint, we want to guarantee that the throughput between the source and destination is greater than a threshold C. Also, we want to make sure that at each of the relay node, their transmission power cannot exceed the maximum transmission power Q. This figure gives some other parameters that might be used in this problem formulation. So the source node will first broadcast the signal to all the relay nodes. And each of the relay nodes, relay 1, relay 2, and relay 3, they can employ any power below Q to amplify and forward their signal to the destination. And we use alpha to denote the signal scaling factor between the source and the relay, and use beta I to represent the signal scaling factor between the relay and the destination node. Our goal here is to minimize P1 plus P2 plus P3, and our constraint is we want to make sure that the throughput between the source and destination is greater than the threshold. Of course, for our mean energy problem, the objective is quite straightforward. The difficulty is how can we formalize this constraint? We actually formalize this constraint based on the rate distortion theory. And let me omit all those mathematical details and directly present the formulation for our mean energy problem. So for our mean energy problem, our objective is try to minimize the total power consumption at the relays. And the first constraint, we try to guarantee that the throughput between the source and destination is greater than the threshold. For the second constraint, we want to make sure that for each of the relay node, their transmission power cannot exceed the maximum transmission power Q. The parameter T here is related to the throughput requirement C, the white noise, and the source transmission power P. Unfortunately, for this mean energy problem, it is a non-convex because the first constraint of this problem is non-convex. So how can we solve this non-convex mean energy problem? We consider to apply an approximation technique called semi-definite relaxation. The original mean energy problem is difficult because of the non-convex constraint. So what we want to do here is we just simply want to relax this non-convex constraint. In this way, we can get a much simpler convex problem. By solving this relaxed convex problem, we hope that we can get an approximated solution to the original non-convex problem. So let's see how we can apply this technique to our mean energy problem. We know that the only non-convex constraint in this problem is the first constraint. So we try to decompose this non-convex constraint into a convex part and a non-convex part. After removing this non-convex part, we will be able to get a relaxed convex problem. Then by solving this relaxed convex problem, we will be able to get an approximated solution. Another interesting property we find when we solve this problem is that, although in general, applying approximation techniques only leads to approximated solution, we find that for our specific mean energy problem, we can actually get an optimal solution to the original problem. So to be more strictly, if we use x cat star to denote the optimal solution of the relaxed problem, we are able to prove that the square root of the diagonal elements of x cat star is in fact optimal to the original non-convex problem. Allow me to omit all those mathematical details and just let me introduce you some of the key steps on how we solved this mean energy problem. The column on the right shows the key steps, and a column in the left shows the key steps, and the column in the right shows the calculation results after each step. So at first, we want to obtain equivalent formulation for our mean energy problem so that we can easily differentiate the non-convex constraint and the convex constraint. So the result is shown in the right. For this problem, we can see the objective function and the first three constraints are all convex. The only non-convex part is the last constraint, which requires the rank of the matrix to be equal to 1. Now we apply the semi-definite relaxation technique and simply remove the last non-convex constraint. In this way, we are able to get a convex problem. And in the final step, we will solve the convex problem. And based on the solution to the convex problem, we are able to get an optimal solution to the original non-convex problem. Now let's look at our mean relays problem. As we have mentioned previously, in the solution to the mean energy problem, all relays will be involved in the transmission. This will cause very large synchronization overhead. So in our mean relay problem, we try to minimize the number of active relays while maintaining the important social link. So again, the source node transmits at power P to all those relay nodes. And for each of the relay nodes, if they are involved in the transmission, they will transmit at power Q and forward their signal to the destination. And alpha I is the signal scaling factor between the source and the relay nodes. Beta I here is the signal scaling factor between the relay node and the destination node. So here we use a binary variable II to denote whether relay I has been chosen to be involved in the transmission. We formulate this mean relay problem as an integer programming problem. So for the objective here, we just try to minimize the number of active relays. And for the first constraint, we are trying to guarantee that the throughput between the source and destination is larger than the threshold. And the second constraint just makes sure that each of the II is a binary variable, only takes value from 0 and 1. This is an integer programming problem. We know that in general, the integer programming problems are NP hard. But this doesn't mean that for this specific mean relays instance, we cannot find in polynomial time optimal solution to it. Here is how we solve this problem. Our basic idea comes from a related problem. Let's consider the case when we are given n packets, while each of the packet has a weight wi. The problem we want to solve is that we want to choose the minimum number of packets such that their total weight is greater than or equal to n. Then this problem can be formulated by this integer programming problem. Although this is an integer programming problem, it actually has a very simple solution. So we just need to rank the packets in the decreasing order of their weights. Then we can simply choose the packets one by one until their total weights are greater than or equal to n. So we are thinking that is there any way that we can rank the relays? If we can find a way to rank the relays, then the problem will be much simpler. So we can simply choose relays one by one until the throughput between the source and destination is larger than the threshold. As it turns out, it is much more difficult to rank the relays because we know that in the previous example, when we rank the packets, when we add one more packet, the increase in the total weight is just the newly added packet's weight. However, here, when we add a new relay, the improvement in the throughput not only depends on the parameter of the newly added relay, but also depends on which relays we have already been chosen. So this is a much harder problem. After some proven calculations, we find that in total there are n squared over 2 different ordering of relays that are all possible. So to be more specific here, if we define a metric A star that is equal to the sum of delta I times II star, we also calculate Aij for each pair of relay. We find that if A star is smaller than Aij, then node I should be chosen first. And if A star is larger than Aij, node J should be chosen first. So let me give you a simple example to see how this works. Basically, in this example, there are only in total 3 relays. We want to calculate Aij for any 2 of those relays. So we will be able to have A12, A13, and A23 here. In the first case, let's consider when A star resides in the leftmost region. That is, A star is less than A12. In this case, relay I should be chosen before relay 2. And relay 1 should be chosen before relay 3, and relay 2 should be chosen before relay 3. So when A star resides in the leftmost region, we will be able to get an ordering of the relays. For all other 3 regions, we are also able to get an ordering. So in this case, If we know A star resides in which region, we will be able to know which ordering is the actual ordering of the relays. Unfortunately, the value of A star is not known a priori. What we can do here is we just want to try all those different orderings and compare the solution of different orderings, try to get an optimal solution. Now let me present you some of the simulation results to see how the mean relays and mean energy strategy works. This figure shows which relays should be chosen under the mean relay strategy. In the figure, the x coordinates and y coordinates represent the location of the nodes, and the red circle in the center is the source node. The blue cross at the upper right corner is the destination node. For all other solid circles, they are relays, and their colors and the color bar represent their transmission power. In the left figure, we can see when the required throughput equals to 0.46. Only two relays should be chosen to help forward a signal to the destination. In the right figure, when the required throughput increases to 0.68, one more relay should be chosen to be involved in the transmission, so that the signal strength at the destination can be improved. In the second figure here, I will show the transmission power of all the relays on the mean energy strategy. Again, the red circle is the source and the blue cross is the destination. We can see that when the required throughput equals to 0.46, all the relays should be involved in the transmission, even though some of the relays are only transmitting at a relatively low power. And when the required throughput equals to 0.46, the maximum transmission power of the relay here is roughly 0.25. And when the required throughput increases to 0.68, still all the relays should be involved in the transmission, and the maximum transmission power of the relay increases to 0.45. Next, let's compare the performance of mean energy and mean relays in terms of the total power consumption and number of active relays. In the left figure, it compares the total power consumption of the two strategies when the required throughput increases. We can see that when the required throughput, that is the x-coordinate, increases, the total power consumption increases. And when we compare the power consumption of mean energy and mean relay, we can see mean energy always performs better than mean relay, because mean energy gives a lower bound on the transmission power to guarantee the connection between the important social pair. Another thing we can notice here is that in the upper right corner, the performance of mean energy and mean relay are comparable, because in this case, all the relays should be transmitting at their highest power to guarantee the connection between the important social pair. So the mean energy and mean relay performs similarly. In the right figure, we show the number of active relays as a function of the throughput, because in the mean energy, all the relays are involved in the transmission. So we can see that for mean energy, under all different values of required throughput, the number of active relays always equals to 30. On the other hand, we can see that for the mean relay strategy, the number of active relays is much smaller than the mean energy. And thank you. Any questions?